Hello everybody. This is our last class on basic Python. Theoretically, last week you just follow a video from NumPy, and you also have the slides of NumPy. Today we are going to practice without NumPy, and I'm going to ask you to deliver a problem implemented with NumPy. So I've been searching for a problem, an interesting problem, and maybe the most interesting is to implement a neural network. I will do it without NumPy. You will get the code without NumPy, and I expect you to do it with NumPy. I will spend some minutes trying to explain how a neural network works, and I will try to implement it using standard Python with lists. So let's go ahead. Let's see how a neural network works. Okay. So here we are. Neural network is a device that has some nodes, something like this. So there is an input and there is an output. And from the input there are some weights here. Weight 1, 1, weight 2, 1, weight 1, 2, weight 2, 2 on layer 1. And here also there are some weight 1, 1, weight 2, 1 on layer 2. So we set some input here. This input goes in this direction, performing some operations, and we get an output here. And which are the operations we see? Let's just make a thumb here. Let's make a thumb here to see how this element works. So let's see how this works. We have this is called perceptron. The perceptron has a set of inputs. There is a plus here. So here we have weight 1, weight 2, weight 3, and so on. Here we have input 1, input 2, input 3, and an extra weight here which is called bias. And this gets inside the perceptron, and the perceptron applies a special function which is called sigmoid, and we get an output. So the equation, how it works, input 1 is multiplied by weight 1, input 2 is multiplied by weight 2, input 3 is multiplied by weight 3, and bias is added here. All these numbers are added, which is the sum of input I, weight I equal to 1 to n, plus bias. And then the special function we apply here is called sigmoid. Sigmoid of x is equal to 1 divided by 1 plus exponential minus x. This function is a little bit special, has this shape. Well, not really this shape, but has this shape. So what we do in reality inside the perceptron is the sigmoid of the sum of I plus bs. This is what we do inside a perceptron. And we have a set of perceptrons here, so the first perceptron we do this, the second perceptron we do this, the third perceptron we do this, and so on. Once you are given some weights at the input, you may do the computations for each layer. So we are going to create a function that performs these operations, and we are going to create the structures that perform these operations, and at the end we are going at least to compute the output of these operations. So if we think on the neural network, we can consider different elements on the neural network. In my case, I'm going to consider we have the network, we have here the input, here we have some weights, here we have some weights, and so also here. So this is called layer. This is a layer, and this is also called layer, and these are the weights of this layer, and these are the weights of this layer. This is also called a layer. This is the output layer, and these are the weights of this layer. So each layer has an input. It turns out that the output of the previous layer is the input to the next layer. The output of the previous layer is the input to the next layer. So I'm going to take advantage of this structure to create the structure of a neural network. And I'm going to do this with Python lists. Let's go ahead. I will make a new file. So here we are. If you are working with Python 2, remember to import division from future. If you are working with Python 3, you don't need to do so. So what I'm sure I'm going to use, import random as random. I will need random numbers to get initial weights on all the network, and import import math, and also import cmath. I import cmath because later we'll take advantage of the complex step derivative to implement the learning algorithm. So right now I'm not going to use it, but later we will use it. So let's try to create a function, define a function that allows me to get a structure of a layer. Let's call it weight. And it has a number of inputs, as a parameter and number of outputs as a parameter. And this will return an array, let's call it layer. Layer is equal to, is a list compression r dot random. Random is a function that gives you a random number between 1 and 0 for element in range number of inputs. And this is going to create all the weights going from the input layer to one single neuron perceptron. As in the second layer I have more than one single perceptron, I need to make this for every output neuron. I'm going to explain that. R random for element 2 in range number of outputs, and this function just returns layer. Okay, let's see if it works. You'll remember this if name is equal to main, then execute this code. I'm going to call the function weights with a layer with one input and one output. Let's see what happens. Okay, I am just forgetting to, I have to save this. I'm going to save it in the desktop, and it's going to be called my simple neural network. R is not defined. Okay, sorry. Random. Wow. Perfect, it works. Let's see what's going on. Let's see the result of this. So I'm going to call this layer. Layer is equal to, here we are, a single weight. Does it has any sense? I guess so. Let's see how is it for one single input output network. So having just one perceptron at the input and one perceptron at the output is like, hey man, you have one input here, one output here, and one single weight here, weight 1. So that's what I got here at the output. Let's see it. Here is my layer, and it just has a single weight. Let's try it more hard. Now I'm going to create 2 inputs, 1 output. So for sure it has weight 1, weight 2. Okay, let's see how it works. 2 inputs, 1 output. Let's run this. Here we are. Here is my layer. My layer is a list which has, in fact, is a list of lists. Take care. When you click here, you get the number of inputs here with 2 weights. The first weight from input 1 to output, the second weight from input 2 to output. Now let's make it a little bit harder. Let's create a neural network with 2 inputs and 2 outputs. That means 2 weights from the first neuron. Okay. That means going to the first neuron, output neuron, there are 2 weights, this one and this one. Yeah. And going to the second network, there are 2 weights also. So let me just get some extra. Okay. Now, so here I have these widths and these other widths. And it's very important to have clear idea on what are the widths. So let's see what happens if I ask for a layer with this structure. So this one is 2, 2. I run this, and I guess I get a layer, and a layer is a list, and each element of the list is a list. So I have 2 weights here and 2 weights here. This is the first element of the list, and these 2 weights here corresponds to these 2 lines here. So in my case, this is 0 dot this is 0.4, and this is 0.68, and the other weights are 0.08, and this one is 0.36. So the structure of this layer is weights going to output 1 and weights going to output 2. Let's try it a little bit more hard, and now I will try to do 3 inputs and 2 outputs. So this will be 1 from here to here, 1 from here to here, 1 from here to here, the first element of the list, and then 1 from here to here, 1 from here to here, 1 from here to here, the second element of the list. So it will be 3, 2. I run this, and I get a list of list, and each element of my list has 3 weights, and these 3 weights corresponds to the next layer of neurons. Output 1, output 2, these are the weights for each output. Perfect. Now I'm able to build a layer. Just let me a moment. I would try to increase the size of the text on my screen. I'm not sure if I will be able. Tools, preferences. It takes some time to open. And here I have the editor. Here we are. No, fonts, maybe here, general. Here we have. Okay, so let's try this on 14 and this on 14. Apply. No effect on the skin. Okay. Yeah. Nice, a little bit bigger. Perfect. Now I'm going to try to go to the next step. And the next step is to create a neural network structure. So right now I'm just creating the weights for one layer, but maybe I want a set of layers. So I'm going to create a new function, define neural network structure, neural network structure, we get as input a list structure, and it will get a list, and it will return also a list with layers. So let's see how this works, and let's try to make an idea. So I say network is equal to new list. Okay, let's create it like this, list. Now it's clear it's a list. Yeah. So I say for element. Now, this is important. Usually you don't try to make for loops over the index, but right now I need a for loop over the index. So for e in range len. I don't know how many layers the user is going to ask for, so I'm going to make it variable len structure -1. So I will create for each element in this list, I will create weights, my function. So the parameters for weight will be structure I, structure I, comma, structure I plus 1. This creates a layer for each pair of elements of the vector structure, and I would just want to keep that information with me, so I will do network dot append this layer. So network will be a list of layers, and the layer is a list of weights. And after doing this, I need to return network. That's it. Okay, let's try that. Let's see how it works. So I will create my neural network is equal to network and I will ask to make a really simple neural network. Right now it will be 1 1. This is a neural network with an input layer of dimension 1 and an output layer of dimension 1. So let's see what we get. There is an extra bracket here. Right. So there we are. Now we have neural network. Python Spider is unable to show that. When you have a list of lists, then it's enabled. But of course we can do here neural network to see which is the shape of this. Okay, let's print it. What? Oh no, I got an error here, sorry. Network is equal a list. Sorry. Don't find this, so I got neural network it's not network, it's network structure. Neural network structure. Let's see. There we are. So let's see what is neural network right now. It says, okay, it has, look at the number of brackets. Look at the manual. It says neural network, outer layer. First layer, the outer bracket. First layer, the middle bracket. The first layer is a set of weights, the inner bracket, and this is the only weight. So this is a very stupid neural network. Let's try to make 2 by 1. Okay, let's print neural network. And it says, okay, you have a neural network right now, outer bracket. It says it has a set of layers, first layer, middle bracket. And in the first layer, you have only one set of weights, this here. Okay, let's try it to 2 by 2. Run. Neural network. Now it says you have a neural network outer bracket. So you see here you opens the middle bracket, here it closes. So you have a single layer with 4 weights. You have 4 weights because it's 2 inputs, 2 outputs. So if you are not sure on this, let's try it a little bit more complex. 2, 2, 2. This creates an input layer of size 2, a hidden layer of size 2, and output layer of size 2. And we are, let's see what we get. So it says, okay, you have a neural network. This is the output bracket. You have a first layer, middle bracket. It opens here and closes here. In this layer, you have 2 inputs. You see it by the number of lists here, and 2 outputs. You see it by the number of columns here. Yeah? And you have another layer with 2 inputs and 2 outputs. Let's try this on 2, 3, 2. Neural network. Here you are. It says, okay, yeah. You have a neural network. Here it opens, here it closes. You have a one, it closes here, and 2, it opens here, closes here. 2 layers, yes. The one that goes from 2 to 3 and the one that goes from 3 to 2. And the first layer has 2 inputs. Here you are. 3 outputs. 1, 2, 3. And the next layer has 3 inputs and 2 outputs. Yeah. Let's try to make a drawing of this to clarify the ideas. So now we have a layer with 2 inputs here, input layer, 3 hidden layers here, a hidden layer here with 3 elements, and an output here. So the external bracket here, wow. The external bracket here says this is my neural network. Middle bracket, fresh layer. It says it goes from 3 to 2. Let's check that. It goes with 1, with 2, with 1, with 2, and this is the first line here. Yeah, it says from neuron 1 to neuron 1, from neuron 2 to neuron 1. Now the next line says and the last line says let's see it. Yeah, there we are. This is from neuron 1 to neuron 1. This is from neuron 2 to neuron 1. This is from neuron 1 to neuron 2, from neuron 2 to neuron 2, from neuron 1 to neuron 3, from neuron 2 to neuron 3. Okay, and now the second layer has 1 here, 1 here, 1 here, 3 elements coming from the intermediate layer to the output layer neuron 1. This will be 1, 1, 1, 2, 1, 3, and 3 other elements in this way. So it is 1, 2, 3 elements, and 1, 2, 3 elements. Let's check that. It says 1, 2, 3 elements, 1, 2, 3 elements. There we are. It's working. Now I have a neural network structure, and my next step is to perform some calculations. And the computations I want to do is for this neuron here, I want to compute input 1 multiplied by weight 1 plus input 2 multiplied by weight 2. And I'm not going to do it, but it should be a plus bias. This is something you will do later by yourself. And also, for instance, for this neuron here, I want to compute input 1, weight 1, input 2, weight 2, plus bias. I'm not going to apply the bias. It's something you will do by yourself. And after making this computation, I will apply the sigmoid function to this. I will add all this, and I will apply sigmoid of x, and this will be this output. And I will do exactly the same here. I will add up all these values x, and I will make sigmoid of x. So it looks to me clear that I need the sigmoid function somehow implemented. And I'm going to implement it in a special way. I will explain later why, but it's not difficult. So let's go back to myself. Okay, perfect. So let's make the sigmoid function, because I'm going to need it every time I compute some kind of weight. So the sigmoid function will be define sigmoid. Sigmoid takes just one parameter, which is x, and sigmoid returns 1 divided by 1 plus exponential, take care, exponential of minus x. I didn't import exponential from CMath. Probably I need here to put math.exponential. But if I use this notation, I will be using the exponential defined on math every time. And maybe at some point, for sure I will want to change that real exponential for a complex exponential. So in my case, I'm going to do this trick. Sigmoid takes two parameters. The first parameter is x, and the second parameter is which is the exponential function. I will say exponential is equal, so I give a default value for exponential, math.exp. And in this way I'm able to compute the exponential. Let's try this. Okay. Here I'm going to compute the sigmoid of number 3, and I'm going to print it on the screen. Print sigmoid of number 3, and I get, okay, that's the sigmoid. Let's try it for number 4, for number 2. There we are. Let's try it for number 1. Yep. Okay, let's try it for minus 10. And you get almost 0. So before I did the drawing of the sigmoid going from minus 5 to 5, in fact it goes from 0 to 5. Yeah? maybe we're going to modify this. Yeah, it doesn't matter. So let's make use of this special parameter I just got here. Let's compute it with a complex exponential. So I can call sigmoid with an extra parameter. The second parameter is the exponential. Cmath dot exp. Now if I call this function, instead of using the standard math exponential, I'm going to use the complex exponential. And there you are. You get the same answer plus a complex part. I'm doing this because if you remember the last time we got class, it was 2 weeks ago, I explained you how to perform the complex derivative. It's a nice trick to compute derivatives with respect to any real parameter. So now I'm going to implement the neural network, and instead of implementing the full backpropagation learning technique, I will just use complex derivative to compute the gradients, and everything will be easier. It's not the most powerful way of doing it. The optimal way is to use the backpropagation algorithm, but I don't have time to explain the backpropagation. So I'm going to do it by hand, computing derivatives with a complex derivative. Now I have my exponential, so I'm in conditions to compute the forward function. The forward function, just for each layer, it takes the weights, the inputs, the weights, the inputs, performs the product, the addition, and calls the sigmoid. Yeah, calling the sigmoid is asking for activation. So I'm going to do a loop over all the weights and inputs of the neural network. Define forward takes two parameters. The first parameter is the input to the neural network. It will input. And the second parameter is who is the neural network to which you want to compute the output. There we are. So this will be something like for layer in let's call this net for each layer in the net, and now for each neuron in the output layer, compute the activation. And activation, we get two parameters. It will be, okay, let's call this network weights. Neuron weights. And if I say nothing, here is a standard exponential. I'm going to be clever. I want to call this from outside, so I'm going to add an extra parameter here. It will be exp equal to math dot exp from exp. So if the user says nothing, this will be computed with the standard exponential. If the user says if the user don't says anything, this will be computed with the. If the user expresses that he wants to use the complex exponential, it will be passed in this parameter. So this will be erased, and it will be passed to this parameter. Okay. I have an error here. Let's see which is the error. Which is the error? Oh, come on. I just forgot here in. So this takes every layer in my net. This takes every neuron in my layer, and this computes the activation. The activation just needs to know who is the input. Who is the input? Take care. One thing is the input to the neural network, and another thing is the input to each layer. Yeah, let's try to explain that. It takes a second to open the board. Here we are. So let's think on this. This is a 2, 3, 1 neural network. So this is the real input to the neural network. This neuron here is a stupid network. It does nothing. It does nothing. And also this neural network. So the input to this layer, is the input. So after some computation, I here get an output. And the input for this layer is the output from the previous network. So out here is input from the next network, and here I will get an output. So somehow I need to record the output of each layer, because it will become the input for the next layer. So let's try to do it. Let's try to save here. Okay, here we are going to create the actual input. The actual input to each layer. And the actual layer input for each layer, the actual input will be equal to the previous output. Yeah. Here I have previous output equal to input. Input is not is a reserved word. Let's call it imp. So first time we get an input, we call previous output is input, and here we call previous. Here we call actual input. And we have to save this. This is the activation out. This is the activation of this, and I have to save it. So in order to save it, I will create an extra layer here. Will be output values is equal to next output values is equal to list. So here I will get output values dot append out. So this just is preparative to get the same code on all the layers. This goes for each layer in the network. This just is preparative to get the same code on all the layers. Previous output, previous output, previous output, yeah, output values. Yeah, this is okay. This is going to store all the outputs from this layer. So for each network, I compute the output of the network, asking for the activation, the actual input to this layer, and the neuron weights using the standard exponential. And I just get the output values and I append this output. Now, when I finish this for loop, I have all the outputs from all the neurons, and I say previous output is equal to output values.